Hello, calculus students. Welcome back to another fun and exciting lesson in AP Calculus. Today we're going to talk about having to take the derivatives of exponential and logarithmic functions. I'm so glad you've made it back. You're through Mr. Brust's lessons for a little while. You can have a Brust break. That's what we call Unit 4. The nice thing is this unit is going to be relatively easy compared to some of the things we've been doing. We're not going to learn any new concepts in this. We're just learning how to take derivatives of exponential functions, logarithmic functions, but nothing new as far as some of those confusing concepts go. So let's get started with remembering what the graph of e to the x means. So I just chose this exponential function, base e. If we were to have that graph, what would the derivative graph look like of this thing? Well, it's positive right here, but it's barely positive. And then as you get up here, it's more and more positive. So the graph has to exist up here. Don't draw what I just did. It has to exist somewhere up here in the positive y values for the derivative graph. So slope is just a little bit positive, a little bit more a bit positive, a little bit more a bit positive, and then really, really positive as you work your way up here. So what that means is that the graph itself will look like this. So the graph of an exponential function is actually itself. E to the x, its derivative is also e to the x. That leads us to, see how nice this is? This is going to be awesome. So if you don't have chain rule and all you have is e to the x, then the derivative with respect to x of e to the x is e to the x. That is as easy as it gets taking the derivative. This is awesome. Then you have this chain rule stuff, because really, how many times can we give you e to the x? That would be just really dumb assignment if we gave you 20 of those. You've got to practice the chain rule. So what that means is if you have e raised to the something else, we'll call it u in this case, and you take the derivative with respect to x, then it's just e to the blah 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 times blah blah blah's derivative. Okay, you'll see what I mean here in just a second. This is good. I think Mr. Brust used a little bit of u in the past, but if not, you're going to see that quite a bit from here on the rest of the year because of chain rule. We'll use u to represent something else that's in this. You'll see what I mean here. Just make sure you have that written down. Let's take the derivative of this one. F prime of x equals, now the derivative of this is just itself, e raised to the 2x minus 3x squared. Look how easy that is. Now we're going to multiply it by the derivative by u prime, e to the u times u prime. So the derivative of this is going to be 2 minus 6x as we apply the power rule. Now typically we'll put this type of stuff in front, but that is the answer there. If this was like a multiple choice type of a problem, most likely they would have this as your answer. They would put that in front and then e raised to the 2x minus 3x squared. But as far as a mastery check or a test goes, like really this, if it's just open-ended, free response, you could answer it like that, and that'd be okay. All right, next one. In fact, I'm going to let you try this one on your own. Pause, and I'll have the answer appear here in just a second. And there's your answer. F prime of x is going to equal cosine x, e raised to the sine x. So again, it's just the derivative of whatever the exponent was goes here, and then we usually put that first for our final answer. Okay, good job. In these first two examples, notice that the base was e, the base was e. Now, not all exponential functions have a base of e. It's very common. Most of this year we'll work with base e's, but sometimes you're going to have a different base. I'm going to call that a base a. So a could be lots of things. A is just a constant. It could be 1, 2, 3.7, but it has to be positive, okay, because it's an exponential function. So it can't be 0. Basically what that means, I can just make this a lot easier. A has to be greater than 0 for this to work. All right, so all you do is you do it's itself again, but then you tag on the natural log of a. In other words, if this was e to the x, think about this for a sec. If this was e to the x, I took the derivative of that. That would be e to the x, and then the natural log of e. Well, the natural log of e is 1. See that? It's just 1. So that cancels out, and you just have this. So we're actually doing it before on this problem with e to the x, but you didn't really see it. So you just have to tag on this extra natural log here. All right, well, what about if you have the chain rule? So if it's a raised to a bunch of blah, blah, blah stuff, you have a to the u times u prime, just like we did before. So you have itself times its derivative, and then you have to tag on natural log of a. So remember, whatever that base of the exponent is, you've got to put natural log of that at the very end of the things that you were working through. Okay, let's do a couple examples. Actually, just one example of this. Find the derivative of y equals 3, y equals 3 raised to the, let's go dy dx this time, raised to 6x. So the derivative of this is itself 3 raised to the 6x times the derivative of 6x is 6 times the natural log of the base, which is a, plus, now what's the derivative of 4? The derivative of 4 is 0. So then our final answer for this one, dy dx, the derivative of y with respect to x, is, let's put this, I said a, oh my goodness. Some of you out there were like, Mr. Bean, you made a mistake. Mr. Bean, stop. Hey, dingling, look. This is natural log of 3 because it was the base 3. Okay, so what can we do with this answer? This is going to become, it really depends on how you want to write this. I'd probably write this as 6, natural log of 3, and then times 3 raised to the 6x. That's probably, the exponential is probably best to keep that last so you can tell that the 6x is the only thing that's up there in the exponent. All right, done with exponential function derivatives. That's it, halfway through the lesson. That's how quick that is. Now let's do logarithms. All right, let's remind you something about logarithm real quick. Logarithms usually have a base. Let's say base 2 of x. If you don't see the base, if I say log x and there's no base there, do you remember what that means? It means it's log base 10 of x. This is called a common logarithm. And then if you see the natural log of x, which is our first example here, if you see the natural log of x, what does that really mean? It means log base e of x. Okay, we're going to use natural log a whole bunch this year, but really what it is it's log base e. All right, so there it is, 1 over x. If you have the natural log of x, its derivative is just 1 over x. Now there's some nice proofs of working through this and figuring it out. We're not going to worry about proofs. We're just going to make sure that you understand that's the derivative, and I'm just telling you, memorize it. But what about chain rule? Chain rule is the natural log of u equals 1 over u, so whatever this blah, blah, blah stuff is, 1 over blah, blah, blah times the derivative of blah, blah, blah. In fact, you also could think of it like this if you really wanted. See how it's this times this over 1? So what does that really mean? You're going to get for the derivative, it would also equal u prime over u. If you think through that, like how this is over 1, so it multiplies. I don't want to confuse you too much, but that's really what is happening there. So it's probably a little easier. I probably better erase that. If you really understand that, go ahead and put it down there. But it's probably a little better to just stick with 1 over x. So this one's 1 over u times the derivative. All right, let's do an example. Okay, here we go. The derivative of f equals, we have the derivative. Whoa, what am I doing? We're going to take 1 over this whole thing right here. So this is going to be cosine of x squared. Let's clean this up. And then we'll say times the derivative of the inside. So the derivative of cosine x squared. Okay, I'm going to write that up here. Now we're taking the derivative of cosine x squared, just to keep track of this. The derivative of cosine x squared is negative sine x squared times the derivative of the inside of that, which is 2x. Holy cow, what is going on? Derivative layers upon layers. See this chain rule stuff? We just got to keep going inside, inside, inside. It's like an onion. You peel back the layers until you start to cry. That's what the chain rule is like. Okay, so then we have, oh wait, let me fix this. You have negative fraction. See, I'm putting this negative in the very front. On top, I've got, let's put the 2x in front. 2x sine of x squared all over cosine of x squared. Uh-oh. What does that mean? We have sine x squared over cosine x squared. Oh, can you remember your rules of trig identities? Sine x squared, cosine x squared, sine over cosine is tangent. So the answer to this is negative 2x tangent x squared. Done. That is the answer. Oh, I didn't even do that one on purpose. That was a good problem. Nice job, Mr. Bean. Okay, number 5. I'm pausing the video. You try this puppy on your own, and let's see what you get here. Okay, welcome back. The answer to this was 1 over 3x. What in the world? If you got this one, you deserve a pat on the back. That is impressive. 1 over 3x. Here's the trick to this. Okay, so we do 1 over this thing, cube root of x, times, now I wrote up here what was on the inside. This cube root of x is the same thing as 1, or x raised to the 1/3. So the 1/3 comes down, subtract a 1, you get negative 2/3. So what does negative 2/3 mean? It just means it's 1 over x to the 2/3. So I brought it down here. So here, this is the denominator. There it is. The 3's in the denominator. There it is here. And then x raised to the negative 2/3 means x to the 2/3 on bottom. Well, x and x are the same bases. So what do you do with exponents when you have the same bases? You add exponents. 1/3 plus 2/3 is 3/3. You have a whole. So it simplifies all the way down to this. That is the derivative. So you can see the calculus part, taking the derivative, that very first step, that's nothing. It's the algebra skills of simplifying these crazy fractions and things. That's where calculus gets a little tricky. Now, just like we had with our exponential functions, logarithmic functions are not always base e. It's not always going to be a natural log. So if you have a different base, like a base 3 or a base 10 or something like that, then this is what you do. You do 1 over x still, so whatever this was, 1 over x times 1 over natural log of a, natural log of the base. Okay, this is real similar to the exponential. Remember, the exponential would be, a to the x. The derivative of that is going to be a to the x natural log of a. Well, this one, since it's 1 over x, it's 1 over x times 1 over natural log of a. All right, what about chain rule? We have 1 over u, so 1 over blah, 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 times 1 over natural log of a. So hopefully you could have figured that out because it's the same thing as here. And then you just have the chain rule. So you have u prime, the derivative of whatever that is. All right, let's do a couple examples and we are done. Logarithm. Let's see. The derivative of this is equal to, so we just, I'm thinking exponential. It's not the same thing. All right, we go 1 over 2x to the 5th times, what do we go next? 1 over, this was not a base e, so we got to say natural log of 4. Now we do the chain rule, times the derivative of 2x to the 5th is 10x to the 4th. So now you can see here you've got a 10x to the 4th that's going to be up here in the numerator, and a 2x to the 5th on bottom. So let's clean up and get our final answer. F prime of x equals, what do we get here? 2 goes into 10, so we have a fraction. You're going to have a 5 on top. X to the 4th cancels with 4 of those x's, so you have an x on bottom. And then a natural log of 4. There we go. All right, try the last one on your own. Pause now. Let's see what you get. Okay, so here's what I got for the derivative. This is where you had to use product rule. Sorry, I ran out of room here. So the product rule, derivative of the first times the second one left alone plus the first one left alone times the derivative of the second. That's where I'm getting this stuff here, the product rule. But then, you know, the question is, well, do you have anything to cancel? If you separate, you got to be real careful here. If you separate with the addition, then we could probably clean this up a little bit. Let me show you what I'm talking about.
So equals 3 tangent x over 3x tangent x natural log of 6. Okay, so this is kind of a pain. Plus, then we do the whole thing again. Sorry, this is so sloppy. So then the other term is 3x secant squared x over 3x tangent x natural log 6. So let's see if this looks any better when we're done. So the derivative then would be, what cancels here? The 3's cancel. Let's use a different color so we can see it. The 3's cancel. The tangent x cancels. So that leaves us with 1 over x natural log of 6. All right, that cleaned up kind of nice. That's a little bit better of a fraction for that first fraction. Then we'll go plus. So then I get the 3x's cancel, but then that's it. So then we get secant squared x over tangent x, natural log of 6.
Now, if you really wanted to get tricky, you could think, well, tangent x, that's the same thing as sine over cosine, right? And if it's on bottom, that means you could multiply by the reciprocal. And on secant squared, oh man, this gets complicated. Secant squared is 1 over cosine squared. And if you bring the tangent up and flip it the reciprocal, instead of sine over cosine, you get cosine over sine. So then you have one of those cosines cancel, and you get 1 over cosine x sine x. Oh my goodness. So you'd have that, and then that is also over natural log of 6. Okay, so that gets a little bit complicated. So there are some things that could simplify, and that's where it comes down to which of these is the correct answer. They're all the correct answer. It's a matter of, if it was a multiple choice test, could you identify that this is the same answer as this one up here? That's where you have to be good enough to know. So we would have these mainly on a multiple choice type of thing where you have to know how to simplify it, okay? But I'd probably, if it was just an open-ended problem, I'd go with this one personally. All right, that's it. You're done with this lesson. Hopefully that wasn't too bad. We're still going to deal with things like tangent lines and the parallel and normal lines and the equations, all that type of stuff. So that can't just go away. We're going to use it all year. All right, rock that mastery check. I'll see you back in the next lesson.